Starting this soon. We're starting this insightful session very, very soon. And for that, may I please request all of us, those who are here and around, to please come inside and take a seat. Ladies and gentlemen, this is the first breakout session, and we are going to have a great learning from this session. So I invite and request all of us, those who are here around and can hear me out, to please come inside and let's take a seat. Thank you so much. Thank you so much. And a very, very warm and wonderful welcome to all of us, those who are here. Thank you. Good afternoon, ladies and gentlemen, and a very, very warm welcome to all of us, all our esteemed guests, our panelists, our speakers, our moderator. My name is Ruchi Singh, and I'm truly delighted to join you all as your MC for the day. And I take immense pride and happiness in welcoming all of us to Second International Conference on Green Hydrogen India 2024. May I please request my August gathering to join our hands and let's get this beautiful day started. Thank you so much. Thank you so much, ladies and gentlemen. Before we move ahead, I would request our panelists. I would request Mr. S.K. Pandey, sir, DGM-Engine Research and Development, Ashok Leyland, sir, to please join us on the dais. Let's give a big hand, ladies and gentlemen. Now requesting Mr. Manoj Karam, Deputy General Manager, Renewable Products and Solutions, Tata Advanced Systems, sir, to please join us on the dais. Now, ladies and gentlemen, please put your hands together and help me welcome Colonel Karandeep Singh, founder and director, FC TecNrgy, sir, to please grace the stage. Requesting Mr. Christian Böhm, Senior Vice President, Defense and Industrial Sales, SFC Energy AG, sir, to please grace the dais. Requesting Mr. DMR Panda, Chief General Manager, NTPC, sir, to please grace the stage. And now, ladies and gentlemen, I am truly privileged to invite our moderator, Mr. Alok Sharma, Director R&D IOCL. Sir, to please grace the stage. Ladies and gentlemen, as we all know, India has set its sight on becoming energy independent and achieving net zero in the near future. To achieve this target, increasing renewable energy use across all economic spheres is central to India's energy transition. Green hydrogen is considered a promising alternative for enabling this transition. In this first breakout session, here we will dive deep and understand the deployment of hydrogen technology for defense sector. As we know, as we all know, several companies like NTPC, IOCL, FCT, and several other are working with Indian Army towards implementing hydrogen application, primarily for mobility and power requirement. In this session, ladies and gentlemen, first we will hear the great insights from the speakers who's gonna talk about the work that company is undertaking for the use of hydrogen in defense sector. Post this, ladies and gentlemen, we will move to the moderated panel discussion where the entire gamut of hydrogen use case would be explored. But before that, we are moving towards the launch of a relevant report. And for that, I would request Shri P. Rahul sir to please grace the podium. NTPC has undertaken a feasibility study. Let's join our hands and welcome Mr. P. Rahul sir on the podium.
Good afternoon to all the guests, the speakers, the dignitaries, the organizers, and the wonderful audience. My name is P. Rahul. I'm from NTPC, and I would like to present you a study that we have done with the generous support of USAID on decentralized power generation for production of green hydrogen using wastewater and its various applications. I'll be very brief in terms of the presentation. So this is the basic scheme, if you see. So we are trying to produce water through two different modalities. I mean, if you see, we are using water or wastewater from a sewage treatment plant, purifying it and then converting into a DM water and then producing hydrogen. The energy required to produce this hydrogen would be coming from distributed solar rooftops on individual households. So this model utilizes the spare rooftop capacity that we have in different cities. Now, in this case, we have done the study for Leh. So the rooftop potential of Leh was analyzed using image processing. The entire city was mapped. Then we could find out the potential of the entire city in terms of rooftop. And then we did actual physical survey or the primary research to find out the willingness of people who will be ready to lend their roofs at a roof rent to a developer, and that developer can aggregate the entire roof capacity and then produce centrally the green hydrogen required. Then this green hydrogen can then be utilized for different applications. So in this study, the relevant application was mobility primarily for the Indian Army at Ladakh, and second was as a backup power for use of different hotels. Now these hotels can project it as a green initiative and would also be ready to pay a premium for the power that is produced. So obviously the prices are a little high because of the nascency of the technology. But however, if there is a gap, even if there is a gap between the conventional cost and the cost from such kind of project would be paid through a subsidy. So for a capacity of 7 megawatt, a subsidy of 30 crore was required in terms of capex subsidy. But if you extend this to the entire Leh potential of having 6,900 households, then there won't be any subsidy required. So this model that we have created is to replicate in different cities. That would not only cater to the rooftop target of the country, but also take this project as a green hydrogen generation project for different cities and different users. you can see there are different households where we can have rooftop solar, and this rooftop solar can be centrally aggregated, and through a net metering agreement, we can actually generate hydrogen. And definitely the cash flow would be, I mean, we would be paying the roof rent to the roof rent lenders, and we'll be getting money from the DISCOM in terms of excess generation that we have. And then the hydrogen that we produce can be utilized in the buses and trucks, and also for backup power in niche segment of the hotels. So here we have also estimated what will be the cost, what will be the subsidy required. If you want a graded subsidy, what can be the rooftop targets that we can take every year. So you will find many things in the report. And this is the executive summary. So 7 megawatt, some subsidy of 30 crore. With 20 megawatt, no subsidy, this project takes off on its own. So this is the QR code for you to download the report. Thank you all. And now we'll be going for the report launch. So I request Mr. Vivek Bharadwaj from USXRF to join us on stage for the report launch.
And now, may I please request all our panelists and moderator, let's come forward, requesting Mr. Rahul sir to please join us at the center. And ladies and gentlemen, may I please request all of us to let's give a big hand as we all take part in launching this very, very insightful report. Everybody, let's give a big hand. Let's join our hands together. I would like to thank Mr. P. Rahul sir. Thank you so much for sharing the great insight. Thank you. And now, ladies and gentlemen, now the time to move forward towards the day. And now I would invite our moderator, sir, Mr. Alok Sharma, to join us on the podium. But before I welcome him, I must tell you, Mr. Alok Sharma possesses a decade of uninterrupted experience in the downstream energy sector. A chemical engineer, alumnus of IIT Delhi, he has made significant contribution to Indian refining sector in process, projects, and production. During his initial tenure at Gujarat Refinery, Mr. Sharma played a pivotal role in establishing India's first hydrocracker unit. Subsequently, he captained setting up the hydroprocessing lab and Retd. During his tenure at Indian Oil and R&D, Mr. Sharma assumed the leadership of the IP cell, significantly enhancing the organization's intellectual property wealth. I would request all of us, let's put our hands together and help me welcome our moderator, Mr. Alok Sharma, sir, to please join us at the podium and set the stage for the day coming ahead. Thank you so much.
Thank you very much. Esteemed panelists, ladies and gentlemen, very good afternoon to all of you. Hydrogen, I think, has become the buzzword now. But would like to mention here that we started way back in 2007. We had set up the first hydrogen station in R&D Center, Faridabad. So a lot of apprehensions were there that why you are doing this. But we started with the hydrogen blending in CNG. And after that, we have come a long way, I will say. And now the traction is there. A lot of push is there on the hydrogen side. National Hydrogen Mission has been launched. A lot of projects are subsidies being given. 19,744 crores of rupees is there for electrolyzer manufacturing, hydrogen manufacturing, then R&D, then steel sector. All the sectors are being covered: steel, shipping, and defense, of course. And even for the R&D projects also, there is a lot of funding available now. And as in the morning, we heard that more than 400 proposals have come. So in that line, we have also submitted a lot of proposals to MNRE, and some of them, I think, are also focusing on the defense sector, because In defense sector, the use of hydrogen and fuel cell is of importance, a lot of importance, I will say, because of the efficiency and the clean and quiet operation which it has basically. And as far as Indian Oil is concerned, we have taken a lot of steps, and we are also supporting the defense forces and other. Though we are already there, and we are our motto of nation first of Indian Oil. We are supporting the defense like forces for all the like lube applications, whatever lube they want. So it goes from Indian Oil. So that way, I think we are already there for supporting the defense forces. And as far as hydrogen and fuel cell is concerned, I will just touch upon briefly on the what we are doing for the defense and what we have done right now. So this is we have developed 15 fuel cell buses, and we are running now currently 2 buses, one with the Indian Army and one with the like naval department. We are going to give 3 more buses, one to the Air Force, and one will be given to the organization, and one to the this Coast Guard also. So we are going to give 5 buses to defense for the defense, like people to commute from one location to other location in Delhi. So rest of the buses are running in other places. So 4 buses will be running in the Vadodara, and rest will be running in Delhi NCR. This is the photograph of the naval, like we gave only last month we have given that, and now it is running. Like other application, as I told you, that reliability and independence, then efficiency and performance, and there are advantages like you can store energy, modular and scalable. So these are the benefits which I will say fuel cell and hydrogen has over like battery applications. A lot of countries are already taken initiatives, and their defense forces are using hydrogen-based fuel cell for various applications. At Indian Oil, we are also trying to develop like the fuel cell for stationary application as well as mobility. We are trying to develop our own, because in the buses, what I showed you, these are all imported. But now we are going for the development of the indigenous fuel cell. I think you will hear from other panelists also that what they are doing in this sector. So this is a special like fuel cell which we have developed for the air, like this for the mobility application. So this is now patented, and we are going ahead for scale up of this. So we have developed at 1 kilowatt, and now we are going for the scale up. We are also trying to develop a hydrogen based cooking solution. So this is also what we are trying to develop, and along with the hydrogen generator as well as the cooking solution for the defense application. So these are some of the projects. And just going in as a summary, I think we are trying to target all mobility, stationary, then even the air mobility, not right now, but slowly will be coming in that also, and cooking applications. So these are some of the initiatives which we have taken, and I think Indian Oil feels proud in partnering with the defense forces. So this is all from my side. I think we'll hear from the others, and then we'll go to the panel discussion. Thank you very much.
Thank you so much, Mr. Sharma, for setting the context for the day. And now, ladies and gentlemen, it's time to welcome our panelists who are going to present their work in brief, how hydrogen is undertaken in defense. Our next speaker, ladies and gentlemen, holds a PhD in mechanical engineering from IISc Bangalore. He has been with Ashok Leyland for the past 20 years and has worked in engine research and development in the areas of diesel engine design, simulation, combustion development, performance and emission testing, as well as overall project management. He is involved in creating alternate powertrain roadmap for future engine technology, which includes hydrogen and methanol economy. Please put your hands together and help me welcome Mr. S.K. Pandey, DGM-Engine Research and Development, Ashok Leyland. Very warm welcome, sir.
Good morning, good afternoon, in fact. So the theme is hydrogen for defense sector. I would primarily speak from H2ICE point of view, although we have the fuel cell architecture as well, but I will focus more on the H2ICE because that makes it more relevant for the high tonnage applications and also primarily for the defense segment. Very briefly on the drivers, as you see, there are three main drivers: climate goals, pollution reduction, energy independence. And for defense, what would be more important would be the energy independence driver part of it. If you see on the bottom side from AL, we have been actually working on the alternate fuel portfolio right from 1994, starting with dual fuels, CNG, LPG, biogas, hybrids, hydrogen plus CNG. And at the moment, as you see, major focus is on hydrogen. For the past 2 to 3 years, we have been working on hydrogen ICE as well as the fuel cells. Very quickly on the H2 ICE vehicle architecture, as you see on the screen, is our avatar vehicle design, which is a modular platform. On the top, you see the diesel vehicle, and on the bottom, you see the hydrogen vehicle. So this is the architecture. As you see in different colors, the orange ones are the subsystems that would actually undergo a change, starting with engine, electricals, fuel system, cooling system, and all that's in the orange color. What doesn't undergo a change is on the right-hand side, that's the green one. And something that gets minutely modified is basically the frame in order to mount the tanks. So that's, in a sense, the architecture of the vehicle, which is not very different from what we have for diesel or a CNG architecture. So it's a scene which is actually doable with minimal changes. What you now see on the screen is actually the fuel agnostic design of an engine. Starting with diesel, how do we go to a CNG engine, and then how do we move to a hydrogen engine? Why we call it as fuel agnostic is because with minimal changes, we can actually use all the three fuels. The change from diesel to CNG is mentioned in the list there. These are the subsystems that undergo change to make it a CNG engine. And from CNG to a hydrogen engine, we again have to focus on the fuel system, piston subassembly, the ignition system, turbocharging, CCV, which is basically the closed crankcase ventilation, EGR system, and some updates for embrittlement, which is prominent in hydrogen. So that's in brief about the fuel agnostic design of an engine. These are our various avatar vehicle platforms with the tank packaging. As you see on the left top is the CNG vehicle, which has a range of R, for instance. And on the right-hand side, we have LNG, which is not relevant to this context. But again, the range is as good as a CNG, that's R. And on the bottom left that you see is the H2I. So the range here is something which needs attention. That's about 0.5 times R. And we need to work on how to improve the range, make it equivalent to CNG. So these are various platforms that we have as on date, and we are working on all of these, which also has the defense equivalents. So we have equivalents of defense. There are 4 different platforms, and these are basically derived from these platforms. A little bit more detail on the 6.3-liter engine that we are working on. So this is the engine that we had showcased in Auto Expo 2023. As you see, this is a 6.3-liter engine. We primarily work on a lean burn strategy because that's manageable for hydrogen. It's a turbocharged engine, which delivers about 900 Newton meter max torque. The after treatment system, as you see on the screen, would be very minimal. It would not be as heavy as diesel. It would be something between a CNG and diesel engine in terms of configuration. The recipe is mentioned on the right-hand side on the table. As you see, each of these unique subsystems, right from fuel injection system, which is an MPFI strategy, we regulate 350 bar tank storage pressure down to 8 bar and use it in the rail. Ignition system or passive coil without ghost ignition, that's very specific to hydrogen combustion. Crankcase ventilation requires dilution along with recirculation. Turbocharging is very specific to hydrogen and needs to be tailor-made for hydrogen. Compression ratios are something like CNG. We spoke about after-treatment system, and there needs to be hydrogen embrittlement updates too. This is our journey in brief. We started with design a couple of years before. We are right now at a stage where we are working on detailed calibration and also starting the validation. Very shortly, we would actually start launching vehicles into the market. This slide, most of you would be familiar. We have partnered with Reliance, and right now 23 vehicles with H2Is are running. They have gathered a lot of mileage, and in fact, one One of them is being showcased in the expo as well. On the right-hand side is our flagship 42-ton haulage that we are working on right now. But it could be anything between 19 tons to 42 ton that this engine can cater to. Very specific to this theme now, the H2Is for defense. So there are 4 different categories: armored vehicles, high mobility vehicles, specialist vehicles, and logistic vehicles. We see a clear visibility to get into the logistic vehicles with this class of engine. If we need to go to the armored vehicles, we would actually have to go to something like 320 horsepower. So that's doable. We have a roadmap that may take another 2 to 3 years of time frame. The challenge in defense would be clearly altitude capability, because the moment you take the turbocharger matching to an altitude, it actually derates. So the altitude capability would be one thing which is very critical, and also the cold starting issues due to water content in H2Is would have to be addressed. So these are some solutions that are available, and we're working on that. So this is what I had to present. Thank you.
Thank you so much, sir. Thank you. And now, ladies and gentlemen, inviting our next speaker. He has over 36 years of industry experience. He has been leading multidisciplinary R&D team in the project design and development industry. His core expertise lies in complex MIL-grade system engineering and embedded system design and development for both the cost-sensitive consumer market as well as high-reliability industrial and defense market. Please put your hands together and help me welcome on the podium Mr. Manoj Karam, DGM Renewable Product and Solution Tata Advanced Systems. Very, very warm welcome, sir, and over to you.
Very good afternoon to my co-panelists and ladies and gentlemen in the audience. So I've been given a short time of 5 minutes to cover this. So I'll be trying to probably go in a fast forward mode. I'll jump straight away to the slides. Over the next 5 minutes, I'll be covering in brief, a very brief history of hydrogen for the defense sector, the opportunities which are available, our expertise, Tata Advanced Systems expertise, what we have developed over the last 8 to 10 years, challenges faced, and of course, some recommendations and mitigations to those challenges. So one would be surprised to learn that hydrogen has been in use in the defense sector since 1861. In the World War I and II, aerostat balloons filled with hydrogen were deployed for surveillance missions and flying artillery adjustments. And the interesting thing is they were so difficult to spot or detect and shoot down that the German Air Force, they actually awarded extra points to their personnel who would be able to shoot it down, because they were at very high altitude, moving very slowly. They just look like a cloud. They're not detectable by missile systems. We talk of in situ generation. Back in 1943, the US Army was actually generating hydrogen in the field using something called an M1 hydrogen generator. It looks like a contraption, an antique piece like this. And this has been documented in the artillery field manual of the US Defense. So they have done it in 1943. I'm sure we can do it better in 2024. These are some of the opportunities in the defense sector. I have broadly categorized it power-wise, from the smallest power to the highest power. If you see portable power units, most of our soldiers nowadays, they're carrying a lot of electronic equipment, communication devices, sensors, night vision goggles on their person. And they need a lot of power to run that. So conventionally, they're using batteries, and fuel cells is a very high potential area where that can be addressed. UAVs, they have a endurance limitation using batteries. Our fuel cells are offering at least 3 times the higher endurance as compared to a similar payload. Ground vehicles, what Mr. Pandey mentioned, there are a number of trucks, artillery vehicles, they all use auxiliary power units, which are basically diesel generators for generating the power. That's one area where fuel cells have been successfully tried. A number of forward posts in the army, field hospitals, they all depend totally on diesel generators. 5 kilowatt, 10 kilowatt. Again, a very high, one of the highest segment of potential in the defense sector. We develop a lot of weapon systems, including artillery guns, launchers and all. All of them require a very important mode called a silent firing mode. Okay, where you want to make sure that the main engine is not running and you're not detected. That is the primary area where a fuel cell can help because of its nature. It's silent. The thermal signatures are very low. Okay, and artillery guns are now also having a lot of diesel generators being used for the silent mode, which can be replaced by the fuel cell system. And of course, the military mobility, where the vehicles, there are a number of vehicles using ICE engines, trucks, 4x4 trucks, armored tanks, which have a potential for the fuel cell system. Same thing if I just categorize in terms of power from top to bottom, starting at 100 to 200 watt, going up to 200 kilowatt per, say, any ICE engine or even a bus, what IOCL has supplied to the army. The biggest segment, what we see is the diesel generator replacement segment in the defense sector. As of 2021, this market was about 1.3 billion and expected to grow to 2 billion in the next 5 to 6 years. Today, as you can see from the graph, a fuel cell solution may cost 8 to 10 times more of a generator. But if you do a cost of ownership calculation, repairs and maintenance, fuel, etc., over a 10-year period, it turns out that the cost of ownership is 50%, half of that of a diesel generator. All over the world, the other armies which have invested heavily in hydrogen fuel cells, US has invested 62 million in hydrogen refueling infrastructure. Korean army has about 800 trucks, 800 armored vehicles, which are all using ICE, and they have already collaborated with Hyundai and Kia, and they are developing hydrogen engines for these platforms. Another important contract which US awarded recently was $10 million for conformal hydrogen storage. As we know, right now, hydrogen storage is all in cylindrical way. But for UAVs and other platforms, you need them to be in the shape to be more optimal. So a special contract for 10 million was awarded to make such storage in conformal, in the shape of the platform itself. A little description about what Tata has been doing for the last 8 to 10 years. So for the last 40 years, Tata has been supplying weapon systems and tactical communication devices to the defense forces. Our DNA being R&D, we decided to start by developing the fuel cell systems indigenously in-house. So as you can see, right from the balance of plant, the PCB design, the complicated stack control strategy, the GUI, communication interfaces, the rugged packaging, everything. Today, we are not making the stack. Okay, I'll tell you the reasons for that also. But other than the stack, everything is made in-house by Tata Advanced Systems. So we started our journey. Our capabilities started with metal hydride, chemical hydride, and now with compressed hydrogen. We are developing a small compact hydrogen generator, which is about 2 kg of hydrogen per day. Sorry. And in the fuel cell side, we have capabilities with open cathode, closed cathode, air cooling, closed cathode, liquid cooling. I'll show you the products which we have developed indigenously in the next slide. These are some of the products, and for the defense sector, there is a important compliance requirement that they must be JSS Penta 5 compliant. They are very strict compliances in terms of temperature, shock, high altitude. Temperature is one of the most strict things where we have to ensure that the system works from minus 30 degrees to plus 55 degrees. And it has to start at that temperature. So one typical test they do is they actually soak your system for 16 hours at minus 30 degrees and then tell you to switch it on, which is one of the toughest tests to perform on a system, on a fuel cell system. And the high altitude operation, which my colleague already mentioned. In UAVs, we have products which can demonstrate 3 times the endurance as a conventional LiPo battery for the same weight. And recently, we have become a technology partner for Mazgan Docks Limited, where a fuel cell ferry was launched. The fuel cell was again indigenously developed by our company, and it was launched by the DefSec in May 24. Compared to an equivalent electric ferry, which gives about 5 hours of endurance, our fuel cell gives 17 hours. And the filling time is just a few minutes as compared to almost 10 to 12 hours, which you have to charge a battery. We are among the first few companies who actually trialed a hydrogen fuel cell at 18,000 feet. I mentioned about, okay. So I'll move forward. So these are some of the pictures. We trialed them at 18,000, 6,000 and all. Again, some more pictures of our trials conducted. This system we recently commissioned at DRDO. It's a standalone microgrid using a fuel cell, solar, DG and a battery and an intelligent power management controller, which we have developed in-house. So we have proved beyond doubt that hydrogen fuel cell is the way to go for defense. Challenges faced. There is a chicken and egg situation. You know, there are 200 hydrogen suppliers and distributors all over India. They say, you show us the demand, we'll reach the hydrogen. The army says, you show us the hydrogen, we'll give you this. So we need to all come together and address that. Today on site, there is no on-site generation. NTPC has initiated the first one. Volumetric densities of cylinders is a little challenge, costs and safety. Most of them we have alleviated. So these are some of our recommendations is that we need a strong partnership between the stakeholders, that's the MOD, MNRE and the industry. IDDM is an important, IDDM and DCPP, that stands for Indigenous Development, Design, Developed and Manufactured in India, and Development cum Production Partner. All of us will agree that we have spent a lot of investment in designing these products, and we need a similar commitment from the MOD to, for production orders. Today, we are willing to spend a lot of money to invest in a stack development or a fuel cell development, but we need those commitments in terms of volumes. In terms of infrastructure, our recommendation is to first have a hydrogen as a service. Install these tube trailers, cascades, and trailers at the site. In parallel, we develop the captive plant model, and the ultimate goal should be piped hydrogen to the forward. Thank you so much.
Thank you so much, Mr. Karam. Thank you. And now, ladies and gentlemen, it's time to invite our next speaker. He's the founder and director of FC TecNrgy. And as we all know, FCT is India's first company to commence marketing and gradually create a small but rapidly growing market for methanol fuel cells in India for defense, homeland security, telecom, oil and gas, smart cities, etc. With over 2,200 fuel cells based solution that includes over 75 hybrid microgrids, FCT is a leading India fuel cell venture today with over 100 employees. The company has already internalized components of fuel cell energy solution and is the final stage of commencing the manufacturing the full range of green hydrogen and methanol-based solution, including fuel cells in India from mid-2023. Please put your hands together and let me call over the stage the founder and director of FC TecNrgy, Mr. Karandeep Singh.
Ladies and gentlemen, my fellow co-panelists, firstly, it's an honor for me to speak to you here today. And what I'm going to cover is basically about how potentially hydrogen and other applications of clean energy can work for the defense sector. So I think I would broadly cover here is firstly something like we're about a 9-year-old venture right now, still very young. We've actually now done about more than actual deployment of more than 2,500 systems in reality for the defense, with orders exceeding over about 75 million US dollars, which the Indian MOD has already spent on these systems. We have about 100 plus professionals purely dedicated into the fuel cell and the hydrogen and methanol systems working across, not only at our facility, but across to support the deployment across the country for the defense. And we've done about 100 plus validations of this technology, from the glacier to mountains to the deserts to, the tropical conditions, the island territories. And that's beyond doubt validates the capability and the potential of this technology as far as the armed forces are concerned. Broadly, we need to understand the requirement of the defense is in two different ways. We have firstly is the field deployment of the armed forces, which is the actual deployment of people who are in the conflict zone, from the glaciers along the Himalayan belt into the high altitudes, or the line of control as far as the Pakistani side is concerned, or the line of actual control as far as China is concerned. And thereafter, we have also a very intense engagement as far as the counter-insurgency or the counter-terrorist operations. So purely the requirement of systems, how they are used, is completely different, whereas the others across the country, as you see on the map, are the stationary applications or the military stations, which are in normal in developed cities along the lines of communication. And as Mr. Karam had brought out, the primary application that you see as far as field is concerned is for field electrification. You have the different types of communication systems that we need: power, drones, UGVs, mobility, and static installations, backup for replacement of generators, radars, surveillance and optronics. These are major and the focus here is basically how do you customize the different types of solutions which are tailor-made as far as the defense, because the requirements are very peculiar. So when you look at how potentially as far as hydrogen would work, before that, I would say, what are the major challenges? Providing power in high altitude, glaciated areas or the field areas is extremely challenging. The current diesel generators or the petrol generators, firstly, reliability is an issue in tough conditions. Their signatures, both acoustic and thermal signatures for military operational environments. Maintenance is again a major challenge, and along with high fuel consumption, pollution, and the biggest issue is the logistics of transporting. We have, gentlemen, about 550 winter cutoff posts, which are cut off for about more than 6 months. So you need to stock up everything for them for 6 months period. So it's not simple, but now using systems which could be based on, say, hydrogen or methanol, you would cut down this logistics anything by 8 to 10 times, which is a huge difference as far as for the armed forces are concerned. Wind profile is not very suitable in the Himalayan region. Either we have no wind or we have very high wind. Similarly, solar for military operations is not on its own an option because of unreliability for 24/7 operations with clouds, winds, monsoons added on. It's not a preferred option. However, a solar could come in as a hybrid. It definitely would make sense, but not as a standalone thing. Batteries, again, a major challenge in extreme climatic conditions, with the lithium-ion batteries not performing in sub-zero temperatures. So again, a huge amount of customization is required. And what I'm trying to bring out here is, as far as the military forces are concerned, you need customized solutions which factor for all these aspects that are peculiar. So now, along with the rest of the nation, the Indian Armed Forces have also set their own emission reduction targets. And that brings in the potential as far as hydrogen and other systems, basically on fuel cells based on methanol and all. And fuel cells have been found now to be an ideal solution to address a range of not only in terms of sustainability, but also in terms of reliability, reducing logistics, and reducing the form factor. And that's what it makes as a very interesting option. When I look at now, I'm segregating as far as green hydrogen is concerned into operational areas and field areas. We've seen from experience, including our interaction with the armed forces, there are major challenges in transportation and storage of hydrogen. Similarly, handling, and it's required specialized people. We have run multiple training capsules over the last 7-8 years. I can tell you, for them to absorb a technology like hydrogen will take years, because the people on ground are very basic They keep changing the rotation. Every 3 months we go, we find a new person there who has to be trained again. So as far as handling complex fuels like hydrogen is a challenge in field conditions. Again, the capex is high. In hydrogen, the opex is also high. The opex is high because of transportation and logistics, not because of other. Not consumption is much low, but you may the transportation and cylinders. Of course, with change in technology, we would have, with the ability of type 3, type 4 hydrogen cylinders coming, you would still reduce it. But at the current form, it is not for field areas because of these reasons, because they are still worried about how do you meet these challenges. Form factor also of an overall infra for hydrogen is substantially bigger than a diesel generator because of these fuel storage conditions. However, and of course, we have efficiency losses. When you're talking about 18,000, the efficiency losses are touching 60% and even sometimes maybe more. However, at the same time, when you look at stationary locations, currently, in the current form, we have well-established infrastructure, a lot of real estate where you can have solar to carry out electrolysis. And therefore, in these areas, we have the option of bringing in green hydrogen as an option for military with buses coming in, transportation in the logistics trucks, and also for replacing generators in these locations. I would say how could be a current way ahead. And this is also something like the way the armed forces are currently looking at. As of now, for the next 3 to 5 years, they were looking at, as far as stationary locations, fuel cell buses. We've just had to see the start in that. Replacement of 15, 30 or 100 kVA generators, power backup for critical infrastructure, net zero complexes in a hybrid with solar or other forms of energy for certain locations like the schools, offices, and comm centers. And at the moment, what we see is potentially a need for going in for pilots. That's what the military is looking at. As far as fields locations are concerned, at the moment, there are big headquarters like Leh, Srinagar, Dimapur. That's where you can still have green hydrogen applications going in. Not recommended for borders, glacier, and high altitude in the current form. Not going forward, but in the current, I would say next 3 to 5 years, where methanol and other fuel cells are far better, which is also globally seen from all the armies in the world. Basically, primarily 90% of the system being used in defense are methanol fuel cells currently in the world. And but 3 to 5 years, we could probably look at with efficiency increasing, cost coming down. And another last thing I would say here is hybrid systems are going to be the way as far as future concerned, where you combine this thing to reduce operating costs, building inbuilt redundancy and other factors. I think I've finished here with the time of this thing. And thank you so much, everyone.
Thank you so much, sir. Thank you so much. And ladies and gentlemen, our next speaker has traveled all the way from Germany to be here with us. He holds over 25 years of global experience in the defense fuel cell market across the US, Europe, and Asia. He holds a bachelor degree in mechanical engineering from the University of Munich and an MBA. And since 2014, he has been leading business development in India. Please put your hands together for our next speaker on the podium, Mr. Christian Robert Böhm, Senior Vice President, Defense and Industrial Sales, SFC Energy AG, Germany. Very warm welcome, sir, and over to you.
Good afternoon also from my side. Thank you very much for the kind introduction and also welcome here to my co-hosts. I'll talk about hydrogen for defense. On the first slide, you see what is our roadmap here from SFC side. You need to know that SFC started as a startup company 24 years ago into fuel cell technology. And as a company, you need to sell products to be successful and to survive. Now, me standing here 24 years after shows you that we obviously successfully understood how to do it and where to do it. And the defense market is and has been for SFC a substantial market. And that's why I'm talking about this in specifically today. Few numbers about the company. I told you already it's founded in the year 2000. We have about 450 employees by today. And we are operating out of 4 locations, one being Gurgaon, very close to here, south of the airport from Delhi, where we do have our manufacturing for the Indian market. And another number I'd like to point out on this slide is 65,000 fuel cells have been in operation from SFC. That speaks for itself. It's for the fuel cell market, a substantial number, and also tells you that we do have a lot of experience operating and deploying fuel cells in all sorts of markets and environments. Here you can see a map where our fuel cells are deployed and where we do have our sales and partnerships. The gray dots here are the operations that SFC owns in Canada from the west side here, US, where we specifically work in the oil and gas and also in the military. Then, of course, in Germany is the headquarter in Munich. We do have our own production of MEAs, which is the core that is located in Swindon in the UK. We have the operation in India, I just mentioned that. And we also, since we do need to expand production-wise also in Europe, in Romania, a new production plant that is actually opening as we speak. On the bottom of the slide, I have listed the defense organizations SFC is working on over the years. Extensively in the United States with all important NATO countries, of course, our home country, Germany, and the Indian Army. I've been visiting India since the year 2014 on a regular basis, and we've been seeing a lot of track also for the Indian defense market for fuel cells and specifically fuel cell products. This slide shows you how we evolved the products. We actually come from the low end, and the gentleman here from TATA already mentioned that this is soldier portable applications. Soldiers do have a need for more power. Everything is electronic communication, visual, satellite communication. So you need a lot of power. Batteries have a limited power density and energy density, and fuel cells have a clear advantage. And these products are deployed since the year 2010 to the different organizations that are already mentioned to you. Then products with higher power, I took out some of those for examples that I'm going to share. And in the recent time, we also hear from the defense side, public security side, a need for fuel cell products with higher power output. And that's why our company is into fuel cell products like the H2 genset that you see here is a mobile application replacing diesel generators, and the hydrogen power pack that can scale up to 500 kilowatts and even more if you scale the product. So summarizing, smaller power, methanol is the way to go. For higher power, hydrogen is the way to go from our experience. A quick word about the technology on methanol fuel cells. We heard that also in the previous speeches. It works on methanol. Methanol comes in a cartridge, in a container. Methanol is also defined as liquid hydrogen because this is a liquid, so it's easy to store, easy to transport. You see the fuel cell. I think that everyone here in the room knows more or less how it works. What is also important to mention is a fuel cell generates DC power. Instead of AC that a generator usually does. And that allows us to hybridize seamlessly with batteries. And that has a huge effect on the overall efficiency that I'm going to point out in one of the following slides. Here you see the military use cases, also very similar to what we have seen before, from portable to onboard power supply to crisis prevention and also dismounted scenarios. I picked out two examples that I'm going into more detail. One is the crisis prevention and also the dismounted and camp size applications. This here is an example that actually we did a study together with the Spanish Foreign League right before COVID crisis happened, 2019. And this is a one-on-one comparison in a military camp. On the one side, using the generator that you see on the right side of the slide, a conventional generator far away from the camp because it's loud. The soldiers actually in this experiment, they were sleeping in the tents overnight over 3 days. And then you see the fuel cell being deployed next to the tent is a methanol fuel cell in this case with a hybridized battery bank. And the key outcome of that study, this is really remarkable, is we used 60 liters of diesel on the conventional side and only 4.5 liters of methanol for the campsites using the fuel cell. And you see the applications that are in here. You have light, you have laptops, you have a heater, you have a coffee machine, you have a printer. So this is what you find in these tents. And that shows you the capabilities of fuel cells being used in the military environment. So it's a huge saving potential. And that also drives the efforts of the various armies around the world to replace diesel generators by modern fuel cell products and systems. The second one I'd like to point out is this is in Germany, crisis prevention. Also, Germany is facing a lot of floodings, unfortunately, also due to global climate change. And the digital network of police, fire brigade, rescue services is a digital network that is has a backup power from fuel cells. Over 1,000 of these sites already been deployed. There's SFC products here inside, as you can see on the cabinet on the right side, and it gives you a reliability of uptime if the power breaks down nationwide for 72 hours to allow rescue teams to do their job and to communicate, which is key in these situations. So these are examples where the fuel cells are today used in significant amounts very successfully. That was my presentation, and I'm sure if you have some questions afterwards, there's some time. Thank you so much.
Thank you so much, Mr. Böhm. Thank you so much. It was really very insightful for all of us. And now we move to our next speaker, ladies and gentlemen. He has over 30 years of work experience in power sector. He has an MTech degree from IIT Delhi. He's the founder of Hydrogen Department within NTPC and is currently leading the green hydrogen in NTPC and is instrumental in undertaking several innovative projects on green hydrogen. He has been engaged in training, learning, and program design and delivery function. Ladies and gentlemen, may I please request my August gathering to join our hands as we welcome Mr. DMR Panda, Chief General Manager, NTPC, over the podium. Very, very warm welcome, sir.
Dear all, see this pic. Now I'm very excited to share with you all what we are trying to do with defense. Now this agreement was raised between NTPC and defense just to explore what is that we can do. Now NTPC is known for electricity and defense is known for what they do best. Now what best we can do? We came out with few proposals which I'll be detailing. Essentially, what we're trying to do is to supply 200 kilowatt round the clock, day and night, without using any conventional source of energy. That's the scheme. And why it is required? Because army personnel are working at such a great height, high elevation, no grade, difficult to take diesel or kerosene or petrol to that location regularly. And coupled with that, the requirement of noiseless operation. Now, this is essentially what we're trying to do. Now, this picture, as you can see, that during the daytime, we will make electricity through solar modules. Part of that goes directly to the load, that is 200 kilowatt during the daytime. The rest of the energy goes into making hydrogen, and that is stored in cylinders, which is converted in a fuel cell to electricity during non-solar hours, evening time, night time. That's the concept. Now, the challenges are many. Why? Because there is no grid. And I'll show you in subsequent 2-3 slides how we are able to work around that. This is a place. Now, the place we are trying to work out the solution is at 5,500 meter elevation. There is no grid right now. No grid will be there in at least 3 to 4 years. And the temperature most of the year, more than 6 months, is sub-zero. And so just imagine what difficult life our friends are having there, fighting for us. Now, this is slightly difficult picture. Just see here. Now, essentially, what is showing here, that is the electrolyzer, there is a battery, and there is a fuel cell. Fortunately for us, when electrolyzer runs to make hydrogen, the other two components are not working. When the fuel cell is working in the night time, non-solar time, other systems are not working. Yet, I need to keep all of them at an elevated temperature so that whenever I need them, they are ready to fire. So that waste heat from the electrolyzer hits the other two during the daytime. During the night time, the waste heat from the fuel cell, which is quite high, hits up the other two, so that all are maintained at a elevated temperature all the time. That's the beauty of the system. And like previous speakers pointed out, so the fuel cell gives direct current output, and so also the solar module. So just to save energy, so we have some solution here. Essentially, for electrolyzer operation, we are taking the direct current from the solar modules so that we save energy on that. Now, this is a very interesting picture, which I am so happy about this and so proud of this. Now, what we are saying, the bottom yellow thing, that's the solar energy. The next one is from hydrogen, and the above one is from battery. Now, why it is so? Because there is no grid. Now, we have designed the system for December and January when the temperatures are extreme. The night time is the longest. Now, the temperatures are very low. Now, as the temperature becomes warmer and warmer, solar duration becomes longer, we make more and more electricity. So the idea is that all the time, all the season, we'll make 200 kilowatt of energy for our defense. The rest of the time, we have some excess energy and we supply them as an extra thing. Now, this is my last slide. You can imagine, simple to see and enjoy and appreciate. It's so difficult. Now, the difficulty level you can understand from this. So there are many components, and that is what NTPC is good at, to manage the complex projects, which are deep technical. Ladies and gentlemen, that is my last slide, and thank you so much.
Thank you so much, Mr. Panda. Thank you so much. And now we have finished all the sessions by a speaker here, and we move towards the most awaited panel discussion. A lot of learning to be shared, a lot of insights to be grabbed for all of us. And this was the session that we all were looking forward to. And now I request our moderator, sir, to please commence the panel discussion.
Thank you very much. Yeah. I think we have 10 to 15 minutes remaining. So I can ask some questions, but I will rather keep the floor open if you want to ask something first.
Like to know, like the high altitudes, you have to maintain the temperature. That means the activation time is less because you all over the time you're maintaining the temperature. But how about the durability of the fuel cell and electrolyzer at the same time? To keep on maintaining at the same high temperature for a longer duration. Do we need to work on changing the anodes and cathodes in the fuel cell?
Yeah, so I understand this question is for me. Yeah, okay. Now, so first of all, we are not 200% confident. Why? Such a system has never worked. But we are very confident that it will work. Why? Because in NTPC, we have been dealing with hydrogen for last 40 years. In all our regular power systems, you need hydrogen in huge quantity, and we are familiar with this. The difficulty is having this temperature, having these equipments running successfully at 5,500 meter up. That's the challenge. And we are very confident. Now, coming back to your question, what about the internals of the electrolyzer and fuel cell? There is no reason why it should not work. So there is no reason why it should degrade faster or later.
even the rare earth metals or longer duration at higher temperature, there are reporting that.
Okay, so if they can work here in Delhi, this location, they can work there. And that is what we are trying to do. We maintain the temperature as it is in Delhi up there around the year.
Thank you, Sir, my question is like you are using methanol fuels as higher altitude, but even at higher altitude, though you have to maintain the temperature. That's the problem which was tried to be solved by Panda in with a larger power station and establishment, but whereas coming to the defense, it is portable, very small. In that case, how do you maintain the temperature?
So I'd like to answer this question in the following way. A fuel cell has a certain efficiency, which is roughly from 35 to 50% of the power that is, or the energy that is in the fuel, in the hydrogen or in the methanol. The rest is unfortunately off heat. But in the situations that you're just describing, when it's very cold, this is a key advantage. So the fuel cell is also producing heat. And what our products do that we sell, if the temperature gets too cold in the fuel cell, there's a sensor and it simply asks the fuel cell to start to generate the heat to protect it from freezing. That's how we do it.
Anti-freeze mode. Yeah. I think I'll further add to what Christian mentioned here. The fuel cell also has an anti-freeze mode. So the anti-freeze mode in these extreme cold climates, in fact, some of our systems, including the SFC systems, have been working in -40 temperatures for 20 years now. And firstly is the anti-freeze mode that makes sure that basically freezing happens. So the anti-freeze mode ensures that all the pumps, the tubes, this thing, and the water is able to move through the system. That's why the system doesn't stop. In fact, even when the fuel cell is, say, for example, not working, say you don't need power all the time. Let's say your battery is topped up for some reason. So that means automatically the fuel cell goes, it doesn't shut down. Automatically it goes on a standby mode. During the standby mode, it makes sure that the internal systems are running so that there is no clogging of due to the extreme cold climates. Further, I mean, because when you go beyond like -30, -40, it is the enclosure which is specially designed under which the fuel cell and the battery are housed. Firstly, you utilize the heat generated by the fuel cell inside the enclosure. And along with that, of course, the battery heat, and that's how this is. And this the enclosure has special, materials and other things which ensures that. So at times the temperature inside the enclosure is about minus another 25 degrees warmer than what it is outside of it.
There is a loss in terms of.
No, what Christian mentioned here is that you would finally get anything from 35 to 45% you would still be getting. And that is from what this thing is there. And like what you talked about derating, derating will happen firstly. We have to accept that there will be a derating. We have tested the systems at, say, let's say from sea level going up anything up to 20,000 feet. In fact, this year early when Mr. Karam mentioned our systems were being tested together at the same altitude, we were together being tested for hydrogen and methanol systems both. And I can confidently say that both the systems work there. Of course, there was derating. The derating at, say, however, I must say, even if it's a 50% derating at 19-20,000, 19-20,000 feet altitude has only probably got about 2% of, but those are very critical deployments of the military which is there. So even with that derating, the applications have been so designed, and this thing is that you make sure that the application that you want to run, you will still get adequate power. But the good part is, at that altitude, these systems consistently work. I will also pass on a little bit on the drone to Manoj. However, what happens, there are two things. Methanol system, if you talk about drones, the drone lift requires very high surge and have a high current. And there are certain applications, but these applications are running basically on, as this is where hydrogen fuel cells come, small cylindrical storage tubes, which is attached next to the drone. And would you like to take it on?
Yeah.
Hmm.
Please give chances to some others also.
Yeah, I think.
Maybe you can talk to them separately. Yeah, please. Go ahead.
Hello.
This one is working.
Hello. Yeah, are there any other questions? Then we can come back to you. Yes, please.
Hello, this is Dr. Prashant Kumar from Indian Oil. I have a question from Pandey sir. Pandey sir. Yes, you have done a very good work in H2Is, and I do believe that you must be having a very good facility for engine test or vehicle testing. So my question would be, you have been testing CNG or other fuels, which is a category of gaseous fuel. So some retrofitment or upgradation of facility you did, or you went through a total green field project. So there are a lot many organizations who want to, come up with H2Is infrastructure.
So this is specific to the H2Is testing?
Yeah, this is specific to the H2Is because, there are a lot of modifications and, a lot of upgradations which are required.
Yeah.
So this was
So we did just upgradation, the existing systems that we had, the existing test bed facility, which are capable of CNG. So primarily we have the storage system that needs to be upgraded for hydrogen storage, get it PESO approved, and all the pipelines have to be compliant to the standards. On the dyno, if you see, the safety systems have to be built in. And apart from safety systems, for sure, the engine-related interfaces have to be
safety system, as in the sensors.
The sensors, also the venting has to be as per the standard. So these were all done based on the existing system only. We did not go for a completely new test bed system.
Okay. How do you see the challenges associated with the H2Is for the cold conditions and high altitude, like the fuel cell?
Okay.
How do you see that?
So two primary challenges that we see is in terms of turbocharging. Even for the ground applications, we have spent, in fact, over a year doing multiple variants of turbocharging, and then we could achieve that. So for high altitude applications, for sure, it would be a tailor-made solution. So it has to be matched as per the requirement, because even at 1,000-meter altitude, we see about 10% deration in power. So certainly for further higher altitudes, we would actually have to have a good turbocharger match. Also for hydrogen combustion, we see cold startability an issue. For gaseous fuels, it should not be. But for hydrogen, there is some amount of water that remains in the combustion chamber. In the next start, we see that it forms a water bridge in the spark plug. So some such challenges are there, but we have some solutions for that, for which we are working.
So you were asking about drones, right? Yeah, what was the specific question about drones?
Use fuel cell in the drone, that's sir said.
Yes.
So safety issue, the weight of the tank, hydrogen tank is higher, as well as when you try to maintain the potential, as Mr. Christian Böhm said, like it's around 40 to 50%. It takes for maintaining the temperature.
So I'll answer it in another way. Today, the technology available for drones is batteries. Okay. At temperatures of -30, -20 at high altitudes, those batteries derate down to 40–50%. Compared to that, if you have a fuel cell, okay, your derating is much less. No doubt it will derate. There's no fuel cell in the world which cannot derate at high altitude. Okay, so it will derate, but comparatively to a battery, it is much less. We have proven during my presentation, I mentioned, an equivalent battery of 4 kg weight, a fuel cell, including the cylinder, including the fuel cell system, gave 3 times the endurance, despite the efficiency losses. But you have to compare with the existing. Similarly, your question about, DGs, although theoretically they say 50%, but in practically we have seen they totally fail. And, in the army, the colonel knows better. They use 3 DGs for one application because they can't run it for more than 8 hours in a day. So after 8 hours, you shift to another DG, another 8 hours, you shift to another. Those limitations are not present in a fuel cell. Yeah, thanks.
Yeah, my name is Rajesh Bade. I'm from Indian Oil Corporation Limited. My question is to Sri Panda. So since solar plant will be producing variable output, so how do you maintain the steady power input for steady generation of hydrogen?
Yeah. You remember that graph with yellow thing on the top? So idea is that we need 200 kilowatt, right? And the solar is for 3.2. So if you understand that curve of solar, so you take the lowest 200 kilowatt during the daytime. So 3.2 is the installed capacity, 200 kilowatt we are taking for the daytime. Rest, all that variable energy, but exceeding 2 megawatt is for making hydrogen.
But During daytime, will it be producing 200 kilowatt at every point of time when sun is
yes,
there?
of course, yes. Yeah, yeah. 3.2. So in a 3.2 megawatt setup, 200 lies in the bottom. Understood, na? Right. Yeah.
Right. I'm Akash. So my question is for methanol fuel cell. So currently, I think, go ahead. Yeah, so I think currently you're using DMFCs in the military application, but do you see RMFC also being used there? Like first question is.
Okay. You can also add RMFCs also can work. However, RMFCs have a very long startup time, firstly, because of the reformer unit which is there. So that is the first thing that happens. Secondly, RMFC in those altitudes and all that is still a little bit of an unknown, because we have personally tested RMFC systems in those kind of climatic conditions. RMFC is a little bit of a still unknown, because you need a very precise mix of 60% of methanol and 40% deionized water. And that's which works on the reformer. Anything which is on any variation there leads to basically a lot of the power dropping and the system going bad, this thing. Then also the other issue is the start-stop cycles are very limited in RMFC. Therefore, the number of times you can start a system and shut down and start it again is limited to something like about, say, less than 100 times. So therefore, that's another reason sometimes but if you want to run a system for a very long time uninterrupted, the system does have its merits. Christian, would you like to add?
I think you said everything. What I can say with confidence, DMFC works very reliably, and this is the key aspect for most of our customers. In secondary, I can say RMFC, for the ones that are not familiar with that, is to make out of hydrogen, methanol hydrogen, and then use this hydrogen in a hydrogen stack. So you have two steps, so it gets complicated. The balance of plant is more complicated, and that comes along with the issues that Colonel Karandeep just mentioned.
Okay, last question. Can I just add one small question? Sure.
Good afternoon, all. I'm Lieutenant Commander Souvik from the Indian Navy. My question is for Mr. DMO Panda. You have shown us how NTPC is working at high altitude in Ladakh mainly. I think you have plant in Chushul, in Leh, Choglamsar. So I had the chance to go to one of the plant in Choglamsar, which was setting up a few months back. So I understand you are putting on bore wells for the water supply, and that where you will electrolyze and produce the hydrogen. But what is the plan for the water? Because Ladakh, we know, is very ecologically sensitive. Groundwater is very scarce. The village, which is quite opposite to that Choglamsar, the water bed is already gone. So what is the plan for that?
Yeah, so plan is that, as you rightly said, we are using borewell as of now, number one. We have taken due permission after studying the data for last 25 years. And the local authority, they are confident that this will be sufficing. And so how much hydrogen we are producing for that hydrogen filling station in Leh? So it is 80 kg per day. So multiplied by, say, 10. So not more than 800. No, we have enough reserve to supply this, number one. Number two, just 500 meters from our location. So Sindhu Nadi, part of that is flowing. So we have enough water.
It will be available for a few months.
Number one. Number two, now the very interesting thing. This is released today. Are you there during that time? Yeah. Now this was released today. What it says, that a very unique study done by NTPC with support of USAID, using the water from the STPs, sewerage water. How we can take that water for making hydrogen through same electrolysis, and that hydrogen would further drive a fuel cell, would drive vehicles. So instead of using fresh water, this report explores that, how this can be done. And through numbers, we have proven that it is sustainable. So this is my answer to your question. So immediate is this is the long term. Yeah.
Yeah.
So I have one question for Mr. Paul. So as you said in your talk, that there is if you're using for small. So if you're using for small systems, methanol is the better one, and if you're using for bigger systems, fuel cell is the better one. So, so what is the range in which we should switch over? And
additionally, I would also say, like, I was getting, I was trying to understand this methanol fuel cell for some time. Some people were coming back, they were saying that after a certain range, the methanol fuel cell maintenance is also a problem or something. So any comments on these two things?
So from our perspective, the switch from the methanol technology to hydrogen is somewhere in between 2 and 5 kilowatts. So everything that is beyond from is what we recommend our customers is hydrogen. Below, we recommend methanol because the handling and the storing is easier. Also, the total costs are usually lower in this range. And your second question is about reliability. We also have to acknowledge a fuel cell is also a technical item that can also fail and break. But what we can say from over 20 years of experience with deploying fuel cells, operating fuel cells, also repairing fuel cells, the moving parts in a fuel cell are much less than in a combustion engine, like a diesel generator. So there is no oil exchange, there is no belts that you need to exchange. All the pumps and fans that are installed are designed for lifetime. Of course, they can break, but usually they don't. And I could say that from overall perspective, the reliability of fuel cells, also from the service perspective, is less compared to diesel generators in general. And there is no difference between methanol and hydrogen. Yes.
Good afternoon. My name is Abhijit. I'm coming from Pune, Electro-Pneumatics and Hydraulics. My question is to the manufacturers of whether you're talking about methanol or hydrogen fuel cells, and you're talking about applications like defense. Now, today, what is the amount of import dependency for these kinds of fuel cells, whether it is methanol or, because since we are talking about defense and we're not trying to scale up, what is the plan for the supply chain development in order to keep on supplying parts or the subsystems for these? So what are the plans for you as manufacturers from the supply chain? Is the supply chain industry geared up? Because once the defense becomes dependent on these systems, are we today geared up, or how much long time it's going to take? So any thoughts on that?
I can say from SFC's perspective, we're a German company, but we have established our facility just last year here to do a local manufacturing. And of course, it's within our scope to also increase the local sourcing, not only from a defense perspective, but also from a commercial perspective, because that saves import taxes and makes us not dependable on foreign sources. Don't know if you want to comment on that.
So, as I mentioned in my presentation, the fuel cells which we are developing, the only one component is imported, which is a stack today. That too will change in a few years because a lot of companies are developing stacks in India. The rest of the components, there are either local sources available, the engineering is completely done by us. SFC is setting up a plant. We already have a plant in India. So it's not a problem. Supply chain, we have been able to find components, multiple vendors for the same component, and established, in the army, there is a concept of, the spares. You have to supply spares along with the thing. So we have to make sure, we have to plan in advance that whatever product you're giving, you are guaranteed or you are committed to give those spares for next 25 years. Unless we don't have that supply chain in place, we'll not be able to meet those commitments to the army.
Last point to here. For the defense, we have set up forward workshops, including in Ladakh and Northeast, stocking them with spares. We have a deployment of almost more than 65 people along the Himalayas. So we can reach almost every location right now. Today, with a maximum lead time of 24 hours, we can reach every system, including in field, which helps in supporting an organization like this.
My last question was again related to methanol fuel cells. So apart from defense, if we talk about the smaller systems which are below like 5 kilowatt, what are the other applications which are like realistic in today's scenario?
So thanks for the question. So defense for us is not more than 10% of the overall market. We do have, for example, in the oil and gas fields of northern Western Canada, a lot of applications, fuel cells that are supporting the SCADA, the data acquisition systems there. A lot of security systems worldwide. City of Singapore is using a lot of fuel cells for that. In the US, in Europe, also in other countries in Asia for CCTV applications. This is a key application. You want to have security more and more. And for that, you need a camera that runs somewhere in between 20 to 100 watts, including data transmission. Then also weather stations, data acquisitions, radio communication in total. So there's numerous applications in this field, and it's a growing demand for that.
Okay. I think, thank you very much. With this, we come to the close of this session. And my thanks to all the panelists and all the audience also for the participation in this panel. Thank you very much. Back to the organizers.
First and most, thanks to all our panelist speakers for sharing such great insight. And thank you so much, sir, our moderator, for conducting it so well. And now the time we move forward and felicitate all our panelists. I would request our moderator, Mr. Alok Sharma, sir, to please join us at the front. Ladies and gentlemen, now is the time we felicitate all our panelists, and we thank from our bottom of our heart for taking your precious time out, coming here and giving us lots of insight. I would first request Mr. S.K. Pandey, sir, to please join us at the front. Ladies and gentlemen, let's give a big hand. Once again, S.K. Pandey, sir, thank you so much for joining. Now requesting Mr. Manoj Karam, sir, to please join us at the center. Ladies and gentlemen, can we give him a big hand? Thank you so much to you, Mr. Karam, for spending time, for joining us and sharing such great insight. Now requesting Colonel Karandeep Singh, sir, requesting you to please join us at the center. And we thank you very, very much for joining us today. And now requesting Mr. Böhm, sir, Senior Vice President, to please join us at the center. And I'm sure he has answered so many questions and we all have learned so much from the session. Now requesting Mr. DMR Panda, sir, Chief General Manager, NTPC, to please join us as a center. We are felicitating Mr. DMR Panda. Thank you so much. Thank you. And now, ladies and gentlemen, Mr. Alok Sharma, sir, I request you to please be joined at the center. And thank you so much for being our moderator and conducting the session all throughout so well. And sharing so much more for us to learn. And we are felicitating our moderator, Mr. Alok Sharma, Director, R&D IOCL. Thank you so much. Thank you so much. Thank you. And to felicitate Mr. Panda is joining at the center. And now may I please request all our panelists, all our speakers to let's join us at the center. It was a wonderful session for all of us. And why don't we give them a big hand, ladies and gentlemen? Come on, come on. Thank you so much. Thank you so much. Thank you. And, we absolutely always believe in capturing the moment. So taking group picture. Thank you so much. Once again, we thank our moderator, Alok Sharma, sir, all our panelists, all our speakers. Thank you so much. Thank you. Wonderful to have all of you here. So much to learn. Once again, thanks to the DMR Panda, sir, Böhm, sir, Dr. Colonel Karandeep Singh, sir. Thank you so much to all of you. Thank you so much, sir. It was wonderful because of you all briefed me so well, so I was able to conduct.